nucleon theory, assuming the meson is stable, so it's sensible. Third, I would guess. Here's the incoming Heisenberg field. Here's two mesons coming out.
Is the way to figure this out just by
Drawing
those?
Yeah.
Calculating only those vertices. Oh, okay.
It's the simplest way.
Yes.
I mean, you could solve the Heisenberg equations in iteration in powers of the infield or something like that and see when, you know, or something like that. But this is certainly the simplest way.
Okay, so it's effectively you say the field produces one meson to begin with, as if it was the free field, and then see what the interaction can do to that meson produced.
Yes, but I mean, this is a point that caused some confusion. Perhaps I should devote 3 minutes to explaining it. We can, by stopping the reduction formula halfway, as it were, develop a Feynman rules for objects like, I will work in a theory which has only got one particle in it for notational simplicity. Sorry. For example, which is the sort of question you want to ask if I take a bunch of fields and hit them on hit the vacuum with them. By the same arguments as led to the reduction formula, but simply stopping before I have at the halfway point, after I've made a bunch of the outgoing particles but haven't started to make the incoming particles yet, for example, I can show that this is integral d4 k1 d4. Perhaps I should call these something different. d4 kn 2 pi to the fourth universal e to the I k1 dot x1. It's the usual reduction formula mess. That's Fourier transforming. Okay. Product I equals 1 to r I minus I PR squared, QR squared is what I called it. QI squared minus mu squared. It's a horrible mess, but when I write it down, you'll see what I mean by it. Gn plus r minus Q1 minus primed minus QR K1 Kn. The point is here I've put some of the fields on the mass shell with the reduction formula. These are these fields here, and I have the factors for them. The other fields I've just left untouched. Okay? If I had put them all on the mass shell, if I had used these to make the incoming particles, then I would have q squared minus mu squared factors for them also, or k squared minus mu squared. I haven't done that. I've left them in position space at an arbitrary point. So a Feynman diagram can represent this kind of matrix element, or of course a matrix element with a bunch of particles on the left and incoming, or mixed things, some incoming and some outgoing and some fields in the middle. And the procedure for getting the diagram for a process of that kind is just the same as the procedure for getting a diagram for an S matrix element, which is an in-state, out-state matrix element, except you only go halfway. You only take some of the lines and put them on the mass shell and multiply by these propagator-killing factors, and you keep the other ones sticking there and free in momentum space or Fourier transformed in position space. So this is, depending on what I do with the external lines, either a well, there's no 1 into 3 scattering, so there's no S matrix element, but a more complicated thing would be either a diagram for a scattering process or a diagram representing all three fields inside the vacuum, or a diagram representing one field between the vacuum and two external particles. Okay? So this kind of object can be deduced from Feynman diagrams, just like an S matrix element can be, or a full Green's function. It's halfway in between. Some of the fields have been used to make outgoing particles, and some of them have been just left lying around as fields.
One other question. Gamma primes as a function, what are the restrictions on p squared, p prime squared, and q squared to make gamma prime be real? You said that it should be real.
When is it real? That's a complicated question. In the theory we have described with those kinematics, it is real at that point. There are cases, you check that if you did the second of the two homework problems, because you found, in fact, it was real aside from a cut beginning at 4m squared, when q squared is left to vary and p squared and p prime squared are m squared. There are all sorts of funny circumstances that can arise, so-called anomalous thresholds, that can arise. There's a whole complicated lore that sometimes makes that point bad. Okay? People who are interested in doing things in a rigorous and general way normally forfeit the physical utility of renormalizing gamma on the mass shell and simply define gamma prime, defining G on the mass shell, and simply define G to be the value of that three-point function when all external momenta vanish. That's the point where everything is guaranteed to be non-singular. If you think of our general rule for getting loops, then all the Feynman denominators are positive quantities, providing there are no non-zero masses in the problem. And so that's a guaranteed wonderful point. You don't have to worry about what singularities may occur before you go on to the mass shell, as in the process of going on to the mass shell. If they're worrying about theories with massless particles in them, they'll even choose a less physical point, where p squared, p prime squared, and q squared are all space-like. And they're guaranteed to have no problems. Okay? It's a technical question and a matter of taste. You have a harder analyticity problem to worry about if you adopt the definition that's most useful from a viewpoint of getting a direct physical meaning. But if you're just interested in fixing your renormalization counter term, you can pick a point where there is no technical problem. Other questions? Well, we now are no longer going to worry about any of those questions of Green's functions and factors of I and k squared minus mu squared that drove all of you batty up until now. They're going to be assumed to be learned things. We'll come back to them eventually and generalize them to the case of spin 1/2 particles. But we'll have at least 2 weeks in which you won't be getting new information of that kind to worry about, but we'll be getting new information of a completely different kind to worry about. It has really nothing to do with quantum field theory, but a lot to do with Lorentz transformations. We are going to construct the quantum theory of spin 1/2 particles. Ultimately, by the end of the lecture after this one, if I keep to my schedule, the quantum theory of the Dirac equation. I do not wish to start out by an approach where I say, well, you all know the Dirac equation, and I instantly begin covering the boards with gamma matrices. I want to derive the Dirac equation as a classical field theory, and then canonically quantize it by our standard machine to find out what's going on. Part of this discussion can be done in some generality that will be useful for subsequent purposes and will also give us additional insight into the structure of the Dirac equation. So I will begin by asking, what is the most general possible transformation properties of a finite number of fields under the Lorentz group, assuming they transform linearly? They just shuffle among themselves. That is to say, if I have a set of fields, phi a of x, and suppose for the moment I have a quantum theory, so I have u of lambda phi x equals some matrix dab of lambda phi b of x, sum on b implied. What are the possible choices for dab? We know there are many choices. There is scalar, for which D is a 1-by-1 matrix in a scalar field. Whoops. Yeah, started out writing a false equation. Lambda inverse x. There is scalar for which DAB is a 1-by-1 matrix and unity. There are vector fields, typified for us by the moment by the derivatives of scalar fields, in which DAB is the 4-by-4 Lorentz matrix itself. There are tensor fields, where it's products of a bunch of those Lorentz matrices, one for each index, which are here all summed up in the superindex A. But what else is there? What are the possibilities? Well, I will phrase this question. I will explore the constraints placed on the matrix DAB by what we know about the matrix U of lambda. In order to keep from writing indices when I don't really need to do it, I'll assemble phi into a big vector and simply write this equation as where phi is some n-component vector and d is some n-by-n matrix, and that's matrix multiplication. It's the same equation with the indices suppressed, which is what going to vector notation means. We have a constraint on U. If I have two Lorentz transformations, U of lambda 1 and lambda 2, then, as I said in a very early lecture, U of the product should be the product of the U's for the individual ones. Actually, this isn't quite right. We know it's not quite right for rotations even, let alone the full Lorentz group, because we're willing to allow spin 1/2. And nature, God forces us to allow spin 1/2 in our theory of the rotation representations of the rotation group. And so really I should say here, I'll put in one side, occasional minus signs are allowed, which we would expect if there were spin 1/2 particles in this theory. I won't bother to write down the general definition of a ray representation, as it is called, and then show that for the particular groups we are dealing with, it can be reduced to just an occasional minus sign. I'll just keep this rigorous argument here, which is what we would do if we'd only have Bose particles, and remind you that we're really a little bit sloppier than that, and we'll also allow minus signs here and there. Now, Bose, falling back into the error of my ancient ways. One of the persistent themes of this course is my trying to remember how to correctly pronounce Bose. Bose is a cow. Bose is an Indian gentleman deceased. Okay. Now, from this and this, we can find a constraint on D. It goes like this. U of lambda 1, lambda 2 adjoint, phi of x, U of lambda 1, lambda 2 equals D of lambda 1, lambda 2, phi of lambda 2 inverse, lambda 1 inverse, x, because the inverse of a product is the product of the inverses in the reverse order. Now, let's write out the same thing using the product equation up there. The lambda 1 thing we can do by assumption. U of lambda 2 adjoint, D of lambda 1, phi of lambda 1 inverse x, U of lambda 2. And then we can do the U of lambda 2, because D is just a numerical matrix. U is an operator in Hilbert space. They have nothing to do with each other. They commute. So we can drag U of lambda 2 inside and obtain D of lambda 1, D of lambda 2, phi of lambda 2 inverse, lambda 1 inverse x. Well, the x is doing rho k, and we see we have the condition D of lambda 1, lambda 2 equals D of lambda 1, D of lambda 2. And again, I tell you that strictly we are working with a looser condition in this, and occasional minus signs are also okay in this equation. Thus, D forms a representation of a finite dimensional matrix representation of the Lorentz group. Thus, our problem of finding what all field transformation laws, all possible field transformation laws, linear, involving only a finite set of fields, and consistent with Lorentz invariance, the problem of finding those objects is equivalent to all finite dimensional matrix. Oh, there's also a condition that makes this, that's needed if this is to be a representation. That's obvious. D of 1 equals 1. All finite dimensional matrix representations of the Lorentz group, which is called by its friends SO31. That makes it sound like a very difficult problem, but as we'll see, it's a very easy problem. Once we have found those representations, we can use them to construct field transformation laws, which from now on we'll think of not as being laws of a quantum theory, but laws for the transformation properties of a classical field before quantization. We'll then select out some particularly tasty-looking fields from these possible laws that have not too many components, but are still look as if they're capable of describing spin 1/2 particles, attempt to construct Lagrangians out of them, quadratic Lagrangians, so we'll get free field theories, and then try and develop a theory of free spin 1/2 particles. Okay? That is the problem, and that is what we are going to do with the answer to the problem after we find it. Are there any questions? If I have used, because of my notorious slovenliness, some mathematical word that you haven't seen before, if there's someone here who doesn't know what a representation is, ask and you shall be answered.
Could you explain it now, what you said, what representations are?
A representation of a group is a set of linear operators, one associated with every group operator, with every group element, that obey these equations. Okay? They multiply like the group elements they represent. Okay? Is that a satisfactory answer? The statement that D of lambda is a representation of the Lorentz group is these two equations. And if it were the rotation group or the 17-dimensional rotation group or the finite discrete group that describes the symmetries of a crystal, it would be the same equation with lambda replaced by the appropriate symbol. Now, please notice that I want D to be finite dimensional matrix, not an infinite dimensional one, but I don't want necessarily want it to be unitary, and I'm not going to apply that constraint. U, of course, back here has to be unitary, but that doesn't necessarily mean D is unitary. For example, if we take the vector field, we know it's not the sum of the 4 squares of the vector, the sum of the squares of the 4 components of the vector that is left unchanged by the Lorentz transformation, but the square of the time component minus the sum of the squares of the space components. In that one non-trivial case, we know D is not a unitary matrix, even though U is a unitary operator down there in Hilbert space. So do not assume that we are looking only for unitary representations. Now, when I say to find all representations, all matrices D obeying these equations, really that's asking a big question that can be replaced by a smaller question, because there are 2 trivial ways of obtaining new representations for old. And one is this. If D of lambda is a representation, which I will write as rep period from now on, so is S D of lambda S inverse for any fixed S. for some s, because it doesn't affect anything in the multiplication. We write, if we have two representations related in this way, we write d of lambda tilde d prime of lambda, and say in words, d of lambda is equivalent to d prime of lambda. Obviously, this transformation just corresponds to choosing a new linear combination of these phi b's for your fundamental fields governed by the matrix S. And of course, we always have that freedom, and we don't particularly care about having that freedom. So that's an infinite way of getting new representations from old, but it's a rather trivial way. So we will restrict our problem to find a set of, to find all inequivalent, that is to say, up to equivalence, reps of O3, 1, finite dimensional. If I were to present you with a table that said, here is the answer, and you found that the table was billions of pages long because I had listed everything obtained from a given one by a transformation of this kind, you would not consider that a very useful table. The second thing is this. There's a second trivial way of making new representations from old. Let's suppose I have two representations. I'll call them now D1 and D2. And this has some dimension which I'll call N1, and this has some dimension which I'll call N2. The dimension of, of a representation by n matrices is n, obviously, the number of fields involved. I can always make a new representation, yes?
Is that S missing there for some reason? S03?
Oh, yes, I'm sorry. Slip of the chalk, thank you. I'm not concerned with parity and time reversal. I will eventually make a few remarks about parity. Time reversal, as always, is a special problem that we'll postpone until quite late. I can build a new representation in the following way. I make a great big matrix. Which in block form has d1 of lambda here, d2 of lambda here, 0 here, and 0 here. This representation, this matrix is given a special symbol. It is called the direct sum of d1 and d2. Can't imagine a more direct way of putting things together. And it's indicated by an addition symbol with a little circle across. Obviously, when this is a representation. When I multiply these things together, d1 never talks to d2, d2 never talks to d1. They just multiply independently. This dimension is the sum of the dimensions of the representation I've put in. It's a bigger matrix. Obviously, I'm not interested in representations that can be written as direct sums. If I tell you I can find a field theory that's Lorentz invariant with a scalar field, and I can find a Lorentz invariant field theory with a vector field, it should not surprise you that I can find a Lorentz invariant field theory that has 5 fields in it, 1 scalar and the 4 components of the vector. A table that contained the possibilities, vector scalar field, 1 scalar field and 1 vector field, 2 scalar fields, 5 vector fields, etc., would also be a useless table. we introduce a concept. If something can be written as a direct sum, if D is a direct sum of two smaller representations of smaller dimension, we say sum, we say, or equivalent to a direct sum, I should say. Since it might not look like this when you first see it as a matrix, you may have to perform some diagonalization. Equivalent to a direct sum, we say D of lambda is reducible. If it is not, reducible, and then we say, to no one's surprise, that it is irreducible. Our problem is not to find all finite dimensional representations of SO31, not merely to find all inequivalent finite dimensional representations of SO31, but to find all inequivalent, irreducible finite dimensional reps of O3, 1. Now, are there any questions about why this is the problem we want to attack? Because once we have solved this problem, we can solve any other problem by a sequence of trivial manipulations. We take the solutions to this problem, stack them up on top of each other, a la direct sum, make some linear transformation if we want to, if we find some other basis for the set of fields to be more convenient, and then we've got the most general object. Now, this is a problem that was solved for the rotation group many years ago, and although perhaps not in this language, it is part of the standard lore of quantum mechanics. Those of you who took 251 from me saw it solved in this language. Those of you who did not, but took some course that had a section in it called Theory of Angular Momentum, saw it solved, although you may not have known, like the man in Molière who didn't know he was speaking prose all his life, you may not have known that you were in fact finding the irreducible inequivalent representations of the rotation group SO3. So let me remind you how the problem goes and how it is solved for SO3. SO3 is the group of rotations. Every rotation matrix can be labeled by an axis and an angle. It is a rotation about some axis by some angle. The angle by convention is always chosen to be less than or equal to pi. If you rotate by more than pi, that's equivalent to rotating by the complementary angle about the opposite axis. We use the multiplication rules of the rotation group to gain information about these matrices D. I will show how that goes. The first step is to observe that if you have two rotations by about the same axis with two different angles, then that's a very easy multiplication to do. You just add up the angles. It's more complicated if the axes are different. This is also true because we are looking for representation. I apologize for the numerous nested parentheses that will appear temporarily. If we take any representation, not necessarily irreducible, just any representation, by the definition of a representation. I will now differentiate this equation. As usual, I'm just doing a review, I could say, but I could also say, as usual, I'm being a slob and will assume everything is differentiable. I will define I d by d theta r d of r of e theta as, by definition, evaluated at theta equals 0 to be e dot j. It must be some linear function of e. This is the definition of j. J is called the angular momentum matrix, or sometimes the generators of infinitesimal rotations. It gives us a leading term if we expand out d for near the identity rotation, which is, of course, theta equals 0, axis equals anything for in a power series in theta. Applying this to this equation, that is to say, differentiating this equation, I'm sorry, I put the theta prime on the wrong side for really doing what I wanted. Do you mind if I engage in some prime transference? Okay. If I differentiate this equation with respect to theta prime and set theta prime equal to 0, I obtain, well, on the right-hand side, E dot j d of r of e and theta. That's just sitting there on the left-hand side. I'm sorry, dyslexia again has taken over. On the left-hand side, I just obtain this because this thing is just sitting here, and I get, I. And I get this. On the right-hand side, differentiating with respect to theta prime and setting theta prime equals 0, and a function that's just the sum of theta plus theta prime, is equivalent to just differentiating with respect to theta. Yes, that's the definition of differentiating with respect to theta, if you want. Add a little bit to theta, differentiate with respect to it, and let the little bit go to 0. This is a differential equation that's trivial to solve, knowing the fact that d of r equals 1 for theta equals 0, and gives us d of r of e theta equals e to the minus I e dot j theta. Unique solution to this first-order differential equation that becomes 1 when theta equals 0. Thus, we've simplified our problem of writing tables enormously. We don't have to tabulate these things for all e's and all thetas. We just have to tabulate 3 matrices, the 3 angular momentum matrices, or infinitesimal generators, as they are sometimes called. Okay. I've gone through this a bit faster than I would if I had thought none of you had seen it before, but there may be someone here who has not seen it before and has become a bit confused. Please ask questions. Okay. Of course, our concepts of equivalence and reducibility also apply here. Obviously, if 2 representations are equivalent, the 2 j's are equivalent. This is logically equivalent to saying that there's some matrix S that turns J1 into J2. And if D1 of R, D of R, equals D1 cross plus, sorry, D1 of R plus D2 of R, then that's logically equivalent to saying J equals the direct sum of J1 and J2. That is to say J1 up here and J2 down here. So as far as checking for reducibility and equivalence, we might as well work with the J's as with the D's.
Did you define also the direct sum of vectors?
I defined a direct sum of matrices. J's are matrices. They are a set of three matrices which I indicate labeled by a vector index. Okay, these are n by n matrices, 3 in number, e.g. sigma 1 over 2, sigma 2 over 2, and sigma over 2. Okay? 3 objects, each of which is a 2 by 2 matrix. Now, do not confuse the vector index on J that tells me what direction we are rotating in with the suppressed indices that tell you how many fields there are and how you sum over them. Now, there is a lengthy calculation that enables you to deduce a very interesting property of the J's. I won't go through it, but I'll write down what it is. You compute the second derivative with respect to theta and with respect to theta prime of a rotation about an axis E by an angle theta, a rotation about an axis E prime with an angle theta prime, the inverse rotation to the first one, the inverse rotation to the second one, whoops, put the bracket, okay, and evaluate the whole thing at theta equals theta prime equals 0. This is a trivial differentiation. You can do this in 3 seconds, and the result, as you can easily convince yourself, up to a minus sign error that I may have done while working it out in my notes, is the commutator of E prime dot j, E dot j. You obviously only get terms of first order in theta and first order in theta prime, so it's going to be linear in E dot j and linear in E prime dot j, and it turns out, because of the way I've stuck things together, it's the commutator. On the other hand, if you know the multiplication rules for the rotation group, now with things along different axes, you know what this object is. It's some representation matrix and some exponentiated j with some axis and some angle depending on theta and theta prime, because this is just the product of 4 rotations. Thus, you can compute this commutator in general from the statement that D is a representation. If you compute it, you obtain, that's the part I won't do, the famous angular momentum commutators sum on k implied. I trust you have all seen the angular momentum commutation rules, even if you may have not have seen this particular way of deriving them. Thus, given any finite dimensional set of matrices that form a representation of the rotation group, they necessarily lead to a triplet of finite dimensional matrices that obey the angular momentum commutation rules. Thus, if we can solve the problem of finding all matrices up to equivalence and direct sum that obey these commutation relations, we can find all representations of the rotation group. We may find some things that aren't representations. I haven't shown you, and I won't take the time to show you, that the process is necessarily reversible. Now, this problem is, of course, a solved problem. The irreducible representation solved by Pauli. Irreducible representations are labeled by an index S called the spin. ds of r is either minus I js dot e theta, where js is some tabulated matrix. S equals 0, 1/2, 1, etc. Dimension, I'll write down some well-known facts. Dimension of ds of r equals 2s plus 1. I trust a known fact to you. Another interesting equation these matrices obey is js dot js equals s plus 1 times the identity matrix. Another interesting fact, the convenient ways of labeling the states are by eigenvalue states in the vector space. I'll now switch to Dirac notation, even though I've only got a finite dimensional space. JZM equals M by eigenstates of JZ. M equals minus S plus 1 minus S plus 2 dot to plus S, the 2S plus 1 values. And the J's, well, it's the simplest ones I'll write down. We'll be using them. J0 is the matrix 0 for all three components. J1/2 is the Pauli sigma matrices over 2, etc. And the etc. you can find worked out in any quantum mechanics books in this M basis, the actual matrix elements of JZ, JX, and JY. And an interesting useful fact is that JS equals JS adjoint. That comes from those tables. That is to say, the J's we can always choose our basis so the J's are Hermitian, which means that the representation matrix is unitary. It's a special feature of the rotation group. Actually, it's a special feature of any compact group, any group of finite volume, like the rotation group, which closes in on itself. Okay, these are known facts about the rotation group. I hope you know them, but if you don't, or if you've seen one of them in some other language and want to ask me a question about the meaning of an equation I've put on the board, ask questions. It turns out that this also solves the problem for the, oh, by the way, I should say, of course, the half integral m's lead to not true representations, but representations with a minus sign in them on occasional places. If you rotate by 2 pi, you don't get plus 1, but minus 1. Double-valued representations, but they're also okay for physical purposes. I will now go through this whole routine here for the Lorentz group. You might think, since you remember you almost got a hernia going through this in 251, that this is a commitment to spend at least 3 hours on this subject. It is not so by a fluke, which we will discover in 10 minutes. Same problem. one subgroup of the Lorentz group is, of course, the rotation group. I will indicate the rotations by the symbol R, even though that's an abuse of notation. R is now a 4 by 4 matrix, which is trivial acting on the time index, not a 3 by 3 matrix, but I hope you will forgive me that. There are also certain other very convenient objects to consider called accelerations, or boosts. A boost in the z direction by an angle phi is defined as the transformation that turns x naught into x naught cos phi plus x3, the z-axis, sinh phi. x3 goes into x naught sinh phi plus x3 cos phi. And should erase more carefully. X1 and 2 are unchanged. Similarly, that is to say, a boost is a pure Lorentz transformation. It takes a particle at rest and moves it into a particle moving with velocity tangent phi along the z-axis. Tangent phi, because if originally x3 was 0, the ratio of these things is tangent phi, and that's the velocity. Of course, similarly, I can define a boost along an arbitrary axis, an acceleration along an arbitrary axis, characterized by this hyperbolic angle phi. A elementary computation shows that we get the following interesting result. Well, firstly, it's trivial standard Lorentz group law that I hope, special relativity law that I hope you know, that every Lorentz transformation can be written as the product of a rotation and an acceleration. So if we know the representation matrices for the rotations and the accelerations, we know them for everything. Secondly, we have defined things with this angle phi in such a manner that A of E phi prime, A of E phi, same E but different hyperbolic angles, is A of E phi plus phi prime. Thus, we can treat the rotations as we treated them before and the accelerations in exactly the same way, simply replacing r's by a's at appropriate points. And therefore, we define 6 sets of matrices arranged into 2, 3 vectors, to wit, the definition of, I will now not call it J because I want to save J for another purpose. E dot L is defined to be I d by d theta, d of R of E theta, as before. E dot M at theta equals 0 equals I d by d phi d of A of E phi evaluated at phi equals 0. We find that d of R of E theta equals e to the minus I L dot E theta, and by exactly the same reasoning, d of A of E phi equals e to the minus I M dot E phi. Now the next step, following closely in the footsteps of our work on the rotation group, is to compute the commutators of L and M. If we know L and M, we know the representation matrix for an arbitrary rotation and an arbitrary acceleration, and by multiplication for an arbitrary general Lorentz transformation. Now, I won't compute them for you, but I'll write them down and try and make them plausible. You can do the computation. It's a short computation. Li Lj is I epsilon ijk Lk. That, of course, is no news. That's because the rotations are a subgroup. Li Mj equals I epsilon ijk Mk. This is not a big surprise. It's just a statement that M transforms like a vector under infinitesimal rotations, just like L. As a consequence of this, but I'll write it down separately because it will be nice to have it, Mi Lj is I epsilon ijk Mk. The minus sign I get from switching I and j being compensated for by the minus sign I get by exchanging the two terms in the commutators. Finally, the only one you have to work at is Mi Mj equals minus I epsilon ijk Lk. That one I leave as an exercise for you to compute. The minus sign is important. If we were doing the four-dimensional rotation group SO4 rather than O3, 1, we could have made almost the same definitions with kashas replaced by sines and cosines, and then we would have gotten a plus sign. To show you that this is at least got vaguely the right shape, let me remark that if the theory we are studying has not only got Lorentz invariance, but parity invariance, need not, of course, but if it did, then we could figure out how L and M transformed under parity. Parity commutes with rotations, and therefore L goes into L. On the other hand, it switches the sign of a boost. If I have a Lorentz boost in this direction and parity transform, I get a Lorentz boost in the opposite direction. So M goes into minus M. Please notice that these commutators are consistent with that. They are unchanged by this replacement, L into L, M into minus M. This one is totally unchanged. This one gets a minus sign on both the right and left-hand sides. This one gets two minus signs on the left-hand side and only a no sign change on the right-hand side. Are there any questions? When I go fast, everyone falls asleep because they can't follow me, and when I go slow, everyone falls asleep because they know it all already. It's a dilemma. Okay. Now, I will now find in one blackboard all the representations, irreducible representations of this algebra. It's based on a special trick. If we were unfortunate enough to live in five-dimensional space, the trick wouldn't work. But fortunately, we live in four-dimensional space-time, and the trick works. The trick is this. I define operators j plus or minus, which are L plus or minus Im over 2. Thus, L is j plus j minus, and M is minus I, j plus minus j minus. Let us compute the commutation rules of j plus and minus. J plus I, j plus j equals. Well, there's a 1/4 from the 1/2. Every term has an I epsilon ijk, so I'll stick that out. And we have everything set up for doing the four terms. The first term gives us Lk. The second one gives us a plus I times Mk. That takes care of the terms with the L in here and either the L or M in here. Now I'll take the M in here. M with an L is another plus I Mk. M with M is an overall minus sign from the I squared, which cancels the minus sign here and gives us Lk. Thus I find j plus I with j plus j equals 1/2 I epsilon ij k j plus k. Of course, the same result would obtain in the same way if I had minus I instead of I in both places. So I'll just write that there. Now what about j plus I I with j minus j? Well, once again, I have a 1/4 on I epsilon ij k. Now let's see. L with L gives me L. L with M, I have the minus on the right, so that gives me minus I mk. L, M here with L here, now I've got a plus I. That's plus I mk. Now the cross term, M with M, I've got I times minus I, which is plus 1, and a minus sign in my fundamental commutators. So I obtain minus LK, or 0. Therefore, yes, sir?
Doesn't look like there should be 1/2 in this equation, should there?
No, there shouldn't be. Thank you. A slip of the chalk. Are there other questions? Thus, we have reduced this apparently formidable algebra into two commuting angular momentum algebras. Exactly the problem we could think about in ordinary non-relativistic quantum mechanics, where we have both orbital and spin angular momentum, both of which obey the multiplication rules, the commutation rules of the Lorentz group, of the rotation group, but which commute with each other. Therefore, it is trivial. I told you I'd do it in one board. It is trivial to write down the answer to what the complete set of irreducible inequivalent representations of the Lorentz group are. They're characterized by two spin quantum numbers, one for j plus and one for j minus. S plus and minus are independent quantities which ran over the range 0, 1/2, 1, ... J plus squared is S plus times S plus plus 1, and J minus squared likewise. The complete set of basis states are given by two numbers, M plus M minus, and J plus or minus, Z, acting on this, is M plus or minus. They are simultaneous eigenstates of Jz plus and Jz minus, which are, of course, commuting operators. M plus and minus run from minus S plus or minus S plus or minus plus 1, up to S plus or minus. Whence the dimension of ds plus S minus of lambda. The number of basis vectors is 2s plus plus 1 for the range of m plus, and 2s minus plus 1 for the range of m minus. Just like L and S, if we had LS without is independent symmetries without any spin-orbit coupling. To make things even more explicit, I'll write down an equation m plus prime, m minus prime, say j plus, m plus, m minus. J plus has nothing to do with m minus, so I simply get delta m minus prime times m plus j sub s plus m plus, and I guess a prime on the first one, where this is the matrix which you will find in any elementary quantum mechanics book full of square roots. You remember that horrible matrix for the matrix elements of J plus. And likewise with plus replaced by minus. Etc. It is just two commuting angular momenta, so there's absolutely no problem in finding the representations. Okay, you've learned something. You now know all the irreducible inequivalent representations of O3, 1. Yes, sir. Fine.
None of these is a unitary.
Well, except for the trivial ones. That's right, because of the I. The I up here. When I make e to the im, I get a Hermitian matrix, not a unitary matrix. But you expected that. I mean, the vector is not unitary. In fact, I'll write that down explicitly. Because we always choose things standardly, so J plus and J minus are Hermitian matrices. M, which is the sum, L, which is the sum, is indeed Hermitian. Rotations are still represented by unitary transformations. But, or working things out explicitly, d of r of e theta is e to the minus I, j plus j minus. I won't bother to put on the S index. You know where that, if it's an irreducible representations, these are the appropriate ones. Dot e theta, d of an acceleration along an axis e by a hyperbolic angle phi is e to the minus j plus minus j minus dot e phi. Now, I'm going to take, now that we have all these representations, we would like to have their properties. Fortunately, since they're all made by compounding representations of the rotation group, about which we presumably know everything from previous courses, we can deduce a whole list of properties from these just by knowing facts about the rotation group. So I'll write down here some facts about O3. And then from these facts, I will deduce a list of facts about DS1, all the representations of O3, 1. The facts I will use will be rather elementary ones. One is complex conjugation. If I complex conjugate a representation of O3, or a fact of any group, not Hermitian adjoint, just complex conjugate, I again obtain a representation because the product of two complex conjugated matrices is the complex conjugate of the product. Of course, since there's only one irreducible representation of given dimension, this thing must be equivalent to ds of r, which means that the matrix Js, because of the I that intervenes in the definition, is equivalent to minus Js star. This doesn't mean we can necessarily write the J's to be real. It just means that there is some transformation, SS inverse on the right and the left, that turns Js into Js conjugate. Secondly, direct product. If we have a set of fields that transforms in the rotations like a vector or a spinner, or something else, some irreducible representation, and if we have a second set of fields that also transforms like some other irreducible representation, we can consider the product of the two fields. This defines a brand new representation of the group called the direct product, and indicated by it's equal to the product. The dimension is, of course, the product, because you now have, you're multiplying two things together, so you have two indices to play with. This representation is certainly something, the product of a spinner field and a tensor field is a something, but it's usually not an irreducible something. And there is a rule for finding what it is, how it breaks up into irreducible representation. It's equivalent to the direct sum, which I'll indicate this way, meaning it's a direct sum, not a numerical sum, where over S, and I'll give you the range of S's in a moment, but I'll write down what I'm summing first, of irreducible representations, where S goes from S1 minus S2 absolute value to S1 plus S2 absolute value by integer steps. Integer, unit, by unit steps. This is a so-called rule for addition of angular momentum, written in a slightly more sophisticated language, and you should know it. Thus, for example, if I multiply together d1 half times d1 half, take the product of two spinners, getting 4 objects, I obtain a d0 plus d1, a scalar and a vector, a one-dimensional object and a three-dimensional object. There's also a sub-item we can add to the direct product. If S1 equals S2, then we can think of exchanging the two objects. It's a sensible question to ask what happens when you exchange them, since they transform in the same way. So we can talk about the symmetry. If S1 equals S2, then D2S, the highest 2S1, the highest one, is symmetric under exchange, as you know, I hope. If not, read an elementary quantum mechanics book. D2S1 minus 1 is antisymmetric under exchange, etc. These are 3 known facts about the rotation group. I presume they are known facts to you, but once again, we may be suffering from linguistic impedance matching difficulties, so if you don't recognize them as known facts, ask the question. A cigarette down here. Looks relatively clean. I'll smoke it. The sterile, I will now take these known facts to find out, investigate 7 questions about things to discover. It just turned out to be 7.
Explain what you mean by that symmetry of the position where S1 is.
Oh. If S1 equals S2, then I can discuss what happens if I exchange the two objects, since they transform in the same way. Okay? Thus, and then I can ask, some of these representations will change sign under the exchange, and some will not. Some will be even and some will be odd. For example, if I put together 2 vectors, D1, cross D1. I know I can make a spin 2 object, which you may not yet know, but you will discover is a traceless antisymmetric 3×3 traceless symmetric 3×3 tensor, a spin 1 object, another vector, which is the cross product, and a scalar, which is the inner product. The symmetric tensor is symmetric under the interchange of the 2 vectors. The cross product is antisymmetric, and the inner product is symmetric. Okay, that means this gets multiplied by +1 when I permute the 2 objects, this by -1, and the next one down the series by +1 forever. Okay? Of course, there's no sense of asking what the symmetry properties are if S1 is not equal to S2, because it makes no sense to say you exchange the 2 objects then. Okay, things I will investigate. 1, complex conjugation. 2, parity. If we have a theory that admits a parity operation, what is the parity transform of a field that transforms according to one representation of the Lorentz group? Transform like. 3, direct products. 4, symmetry. If the 2 representations are identical, what's symmetric and what's not. 5, what happens when we restrict the rotation group, the Lorentz group, to the rotation group? If we have a big representation of the Lorentz group, it's also a big representation of the rotation group, but it may not be irreducible. How does it fall apart if we restrict the Lorentz group to the rotation group? 6, for example, a vector falls apart into a scalar and a 3 vector. 6, where is the vector, by the way? I've been talking about it. What is it? Is it 7 halves, 4 halves, or, what? Well, we know the ordinary vector is a representation of, a irreducible representation of the Lorentz group. Where is it in our catalog? And also, where are the tensors? They're also representations.
What do you mean when you say
I mean, sorry, this is qualitative. What S plus S minus do we assign to the vector representation? Where is it in our catalog? Somewhere in our catalog it should say representation S plus equals such and such, S minus equals such and such, parentheses, all alias vector. Where is it? Now, I doubt if I will have time to do more than 6 of these things in the 15 minutes remaining. But let's work them out one after another. Actually, they're all very fast because we know the answers. We've just got to put the things together and keep track of these i's and so on that go on here. Come on, you can't say it's boring. It may be obscure. It's not boring. A man who is tired, as Dr. Johnson said, and slightly differently in another context, a man who is tired of group theory is tired of life, sir. No. I made a killing. You get a good salary. It's all done with group theory. We're thinking of advertising on matchbooks. Learn how to make $20,000 a year through group theory. But then the job market collapsed, so the whole scheme fell apart. Enough of this frivolity. J plus and minus are ordinary rotation matrices, ordinary angular momentum matrices. And therefore, for some particular, they are equivalent to their minus their conjugates by the equation written in this right here. They're each one of these JS's. Therefore, L, which is their sum, is equivalent to minus L star. But M, which is minus their difference, is equivalent to plus M star, sorry, because of the intervening I. Now M is also J plus plus J minus. J plus minus J minus, as we see here. Sorry, phrased it badly, minus I. J plus minus J minus. Therefore, the disgusting sign that appears here that would keep D from being equivalent to its conjugate can be canceled out if we exchange J plus and J minus. Therefore, we deduce D of S1 comma S2 of lambda is equivalent under complex conjugation to D of S2 S1 of lambda. The effects of complex conjugation can be canceled out up to an equivalence transformation by exchanging J plus and J minus. Notice, therefore, funny business is going on, that if I have a set of fields and they transform in a certain way, their complex conjugates do not transform in the same way unless S plus, why did I write S1 and S2? I wrote S1 and S2 out of perversity. S plus, S minus, S minus, S plus. The complex conjugates do not transform in the same way unless S plus is equal to S minus. Parity. Parity, as I stated before, if it is defined, turns L into L and M into minus M. Again, turning M into minus M is an operation that can be thought of as exchanging J1, J plus, and J minus. Equivalently, we could say parity exchanges J plus and J minus. Thus, if we wish to have a parity-conserving theory involving only fields that transform according to the representation 3/2, 1/2, we have the chance of the proverbial snowball in hell. A parity acting on a field that transforms field that transforms like ds plus s minus of lambda must make a field that transforms like d s minus s plus of lambda. On the other hand, parity plus complex conjugation gives us a field that transforms in the same way, and we will see later on this will make it easy for us to construct theories that are CP invariant but neither C invariant nor P invariant. A nice thing for weak interaction theory. Onwards. They're all trivial. The only hard one is 7. I may run 5 minutes over time and do 7 also. I hear whispering. Is there questions? I say I flip around. Questions? Any questions? I'll shoot you. Direct product. Well, this is again trivial. We've got two independent angular momentum. we add them together independently. There's no problem. ds plus, what do I call it, 1, s minus 2 of lambda, s minus 1, thank you, cross d s plus 2, s minus 2 of lambda equals the sum of them s. S plus goes from s plus 1 minus s. It's harder to write out than to explain, isn't it? From the difference to the sum. S2, s minus, does the same thing. Version destruction across the board. Where s plus and s minus go by unit steps independently between the lower bound and the upper bound. There's two angular momentum that don't talk with each other, and they add together and still don't talk with each other. Symmetry. Which, of course, is reasonable to discuss only if the two things are equal, just as before. Well, if you exchange them, you exchange both the s plus and the s minus part. So if it's symmetric if the two parts are individually symmetric, or if the two parts are individually antisymmetric, and antisymmetric in the other case. Thus, s plus equals 2s plus 1. S minus equals 2s minus 1 is symmetric. S plus equals 2s plus 1. Didn't write very well. Minus 1. S minus is unchanged. Is antisymmetric because it's antisymmetric in the first variable and symmetric in the second. Likewise, s plus equals 2s plus 1. S minus equals 2s minus. Minus 1 is ditto, antisymmetric, etc. The symmetry and antisymmetry is exactly what you would expect for a product structure. Any questions? Question 5. What happens when I reduce the SO31 to SO3? That is to say, if I just look at the rotations. Any representation of a big group is a representation of some small subgroup, but if it's an irreducible representation of the big group, it might not be an irreducible representation of the small subgroup. Well, this is again the same formula, because we have, for just a rotation, sorry, switched my notation. Thus, if we just restrict ourselves to rotations, if we think of J plus and J minus as being like orbital angular momentum and spin angular momentum, it's as if we have coupled orbital angular momentum and spin angular momentum and only consider the combined rotation group, simultaneous spin and orbital rotations by the same angle. Well, this is just our direct product formula again. So I have ds plus s minus of r, restricted now to rotation r, is equivalent to the sum of the ds of r, representations of the three-dimensional rotation group, where s goes from s plus minus s minus to s plus plus s minus, and of course this is a direct sum. And just all I'm talking about is rotations. Now the fact that these two independent angular momentum came from the Lorentz group is totally irrelevant. Problem 6. 7 questions, but they all have simple answers. 6. Where is a mu is a vector. It certainly defines a representation of the Lorentz group. That representation is pretty obviously irreducible. So it must be somewhere in our catalog. That is to say, the vector must be some represent. What do we know about a vector? Well, firstly, we know it's 4-dimensional. So 2s plus plus 1 times 2s minus plus 1 must equal 4. Since both of these numbers are integers, there is not too many solutions. To be precise, we have possible solution, s plus equals 3/2, s minus equals 0. That's 4 times 1. And it's obviously no good because it's not equivalent to its complex conjugate, and a vector obviously is. Also, it doesn't admit a parity, and a vector certainly does. No good. Complex conjugation. We have s minus equals 0, s plus equals 3/2. That's also no good for the same reason. Whoops. Finally, we have s plus a fortiori for the same reason. S plus equals s minus equals 1/2. This is the only possibility, and as Sherlock Holmes used to say, therefore it is the right answer. So the vector, a vector field, transforms according to the 4-dimensional irreducible representation, d 1/2, 1/2. Let's check that by using our previous result. Check. Is equivalent to d1 of r plus d0 of r by the formula on the center board. 1/2 plus 1/2 and 1/2 minus 1/2. This, as I hope you know, is a 3-dimensional 3 vector. And this is, of course, always and forever a scalar, a single number that doesn't transform. Is this indeed what happens to a Lorentz 4 vector when we restrict ourselves to rotations? It certainly is. The time component is unaffected by rotations, and the 3 space components transform like a 3 vector. So it all pulls together. Checks. Now, once we have vectors, we can have tensors, because tensors, rank 2 tensors, which all I'll talk about, are direct products of vectors. And by figuring out our formula, we can figure out how various tensors transform, rank 2 tensors. But I will talk about that at the beginning of next lecture because we have run over time. And also at the beginning of next lecture, we will start building field theories from some of the simple representations that we have found here, in particular 1/2, 0, and 0, 1/2.